Hi, everybody. So now that we have some examples of homomorphisms, let's establish their fundamental properties. And as we'll see, the basic idea is that when you have a homomorphism from one group to another, what happens is the image is a subgroup of the bigger group that you're landing in. And so in some ways you can think of this, it's not an isomorphism, but it sort of sticks the group G inside the group H, but not all of the group G, only a kind of a compressed version of G. So let's see if we can make any sense out of that rather vague statement. So I'm going to walk through proposition 11.4 in Judson's book, and we're going to start with a homomorphism phi from G1 to G2 and work through its properties. So the first property of this homomorphism is that it carries the identity element of G1 to the identity element of G2. And this was true for isomorphisms as well, you'll recall. And it turns out that you can prove it even in the weaker case of a homomorphism. And the proof goes something like this. So let's let E2 be the identity of G2 and E1 of G1. And by definition, we have that E2 times whatever phi of E1 is, it's an element of G2. So E2 times phi of E1 has to equal phi of E1. But phi of E1 has to equal phi of E1 times phi of E1 times E1, because in G1, E1 times E1 is the identity. And by the homomorphism property, that has to equal phi of E1, phi of E1. So here we're using the identity in G2. Here we're using the homomorphism property. Here we're using the fact that E1 times E1 equals E1. Here we're using the homomorphism property. And if you look at these two equations, using cancellation, we can cancel, let's use a different color for the cancellation just for fun. We can cancel the phi of E1 on both sides of this equation, and we're left with E2 equals phi of E1, which is what we were trying to show. So for a map to be a homomorphism, it has to carry the identity of the first group to the identity of the second. It also has to carry inverses to inverses. So if G1 is an element of G1, then if you take the inverse of G1 and apply phi to it, what you get is the same as if you had first applied phi to it and then computed the inverse. And the proof of this is kind of similar to the little trick that we just did a minute ago, because we know that if you take phi of G1 and you multiply it times phi of G1 inverse, so these are elements here in G2, then by definition, this is equal to E2, right? Because it's the identity element in G2, but we just showed that's equal to the phi of E1, and that's equal to phi of G1 inverse times G1, because G1 inverse times G1 is E1. And by the homomorphism property, that's phi of G1 inverse phi of G1. And then we do the same trick that we did in the previous problem, previous result. We can cancel this phi of G1 and that phi of G1. And the result that we get is that phi of G1 inverse on this side is equal to phi of G1 inverse on that side. Now, this may seem very formal, but it's worth pondering a little bit, just maybe one more time what it actually means. You have two groups, G1 and G2. Here they are, G1 and G2. And you have an element of G1, and you want to know what it's, and you want to know, here we have this map phi, and you also have its inverse. So you could go from G1 to G inverse, G1 to G1 inverse in G1, and then go by phi to G2, and you would get phi of G1 inverse. Or you could go across to G2 first and get phi of G1, and then take the inverse here, and you would get phi of G1 inverse. And you get the same answer both ways. So these, in some sense, these operations commute, taking the inverse and applying phi. Just like before, for the identity, it was preserved. Okay, so now using these two facts, we can prove the first thing that I mentioned, which is that if you have G1 going to G2 by phi, and you take the image, and you have a subgroup here, and you take its image, it's also a subgroup. So remember, that phi of H1 is the set of G2 in G2 such that G2 equals phi of H for some, maybe I'll put the H1 in, some H1 in H1. It's the things, if you want another picture, here's G2, here's G1, here's H1, here's this map, here's phi of H1, it's the things that get hit by H1 under this map. And the claim is that that's actually a subgroup. If you start with a subgroup and you apply phi to it, you still get a subgroup. And remember that we have a standard proposition. We have to show that if X and Y are in phi of H1, then so is XY inverse. And that's enough to show, we have to show that H1 is non-empty. So why is H1 not empty? Sorry, phi of H1. So phi of H1 is not empty because E is in H1, E1, the identity element of G1 is in H1. H1 is a subgroup. And so phi of E1 is in phi of H1. So H1 is not empty. It contains the identity element. Remember, this is E2. So now we can use the criterion. So if we take X and Y in phi of H1, we know that X is phi of H1 and Y is phi of H2 for some elements. And then XY inverse is phi of H1, phi of H2 inverse. And now we use the previous fact to convert this to phi of H1, phi of H2 inverse. And then we use the homomorphism property to write this as phi of H1, H2 inverse. And then we use the fact that H1 is a subgroup, so H1, H2 inverse, H1 and H2 are both in H1, so H1, H2 inverse is in H1, so XY inverse is also in phi of H1. And so we know that a homomorphism takes G and puts it inside the other G1, puts it inside G2 as a subgroup, although it's not an isomorphism onto its image. And exactly what happens in that process is something that we'll look at in a little while. And it's true in the other direction as well. Namely, if you have G2 and you have a subgroup G2 of H2, and you take its inverse image or its pre-image. So remember, the pre-image of H2 is the collection of H in G1 such that phi of H is in H2. So it's the things in G1 which land in H2. And the claim is that that's a subgroup. And we'll use the same criterion that we used in the previous problem. So first of all, we need to know that phi inverse of H2 is not empty. But since E2 is in H2, phi inverse of E2 is in phi inverse of H2. So phi inverse of H2 isn't empty. I mean, basically this is just saying that H2 isn't empty because it's a subgroup. And then let's suppose we have X and Y in phi inverse of H2. So we're going to have to check the same thing that we checked a little while ago. So choose. So that means that X is phi of A and Y is, sorry, phi of X, let's write it this way. Phi of X is A and phi of Y is B, and A and B belong to H2. That's what it means to say that X and Y belong to phi inverse of H2. It means that if you apply phi to them, they land in H2. And now we do the same calculation as we did before. We do phi of X, phi of Y inverse. That's AB inverse, which is in H2. And therefore, using the same ability to move the inverse into the Y and then combine using the homomorphism property, we get phi of XY inverse equals AB inverse. And that tells us that XY inverse is in phi inverse of H2. Because its act phi of it is AB inverse, which is in H2, and that's what that boils down to. So both the image of a group under a homomorphism, image of a subgroup under a homomorphism is a subgroup, and the pre-image of a subgroup under a homomorphism is a subgroup. And the last point, which will be very important for our applications, is to notice that if you have a normal subgroup, then the pre-image is also normal. So remember that H2 is normal. This is from our last section, means that GH2 G inverse equals H2 for all G in, let's put the 2's in, all G's in G2. And we want to show that G1 phi inverse of H2 G1 inverse is phi inverse of H2 for all G1 in G1. And that'll tell us that phi inverse of H2 is a normal subgroup. So let's suppose to do this, we choose an X in phi inverse of H2. So that tells us that phi of X is equal to A, which belongs to H2. And if we look at G1 X G1 inverse, or G1, then let's apply phi to that. So that's phi of G1 using the homomorphism property, phi of X, phi of G1 inverse. That's a phi. And notice that phi of G1, and let's just call that G2. It's just some element of G2. And phi of G1 inverse is G2 inverse, where again, we're using the fact that homomorphisms commute with inverses. So phi of G1 inverse is the same as phi of G1 inverse on the outside. So this equation here can be written G2A G2 inverse. And by this normality hypothesis for H2, this belongs to H2 as well, because A belonged to H2. In other words, we just showed that phi of G1 X G1 inverse is in H2, which is the same thing as saying that G1x, G1 inverse is in phi inverse of H2. In other words, we proved that take any element of phi inverse of H2, hit it with any G and G inverse on opposite sides, and the result is still going to be an element of phi inverse of H2. And that means that phi inverse of H2 is normal. Okay, our next topic is kernels, and I think we'll take that up in the next video.